Thank you again. And I mean, in a certain sense, Singapore is responsible for the fact that I'm in quantum information, because the way I got interested in it, Vlado Buzek ran a number of conferences in a shack near Bratislava, Slovakia. And in the early to mid 1990s, one of the speakers was a graduate student of Arthur Eccles. Okay. And is Arthur still connected? Yes, if he is, okay. I haven't seen Arthur in quite a long time. Anyway, so his student gave an absolutely fascinating talk on this new subject of quantum information, which I had never heard of before. And I found it absolutely fascinating, and talked to Arthur afterwards, and he sent me a stack of papers like this, and I actually read all of them, and then just started thinking about quantum information, and without even trying to, I ended up switching fields. So let me tell you today about one of the results of that. So if you don't like this talk, you can blame Arthur, all right? So that is a picture of Hunter College. It's 3 15-story buildings on 3 out of the 4 corners of one intersection of Manhattan. So what I'm going to tell you about today, I'm going to give you a brief history of wave-particle duality relations. And then, as Berge said, I'm going to talk about quantum resource theories, in particular entanglement, asymmetry, and the one that we're really going to be paying attention to is coherence. And then the idea is applying some of these things from the coherence resource theory, in particular coherence measures, to wave-particle duality. And then further application is something we call the wave-particle duality game. Okay, I think this notion of games has been introduced by computer scientists into the quantum information field, and it turns out to be an extremely useful one. Okay, so let's begin at the beginning with Bohr and Einstein. So Einstein thought he had a way that you could get both path information and an interference pattern at the same time. His idea was the following: you have a particle coming in, you have your usual 2 slits, and then they proceed onto a screen, but the catch is that the screen with the slits could move up and down, all right? So the idea is if it goes through one slit, it'll give this screen one kind of a kick. If it goes through the other slit, it will give this screen another kind of kick. And Einstein maintained that by measuring the kicks that were given to the screen, you would be able to tell which path it took, and then the photon would simply proceed onto the second screen and produce an interference pattern. So this was one of those things that probably gave Bohr a sleepless night, and then he showed that if this thing can move, it obeys the uncertainty principle. And excuse me, in order to tell which slit the thing went through, you have to have a resolution, momentum resolution, given by hs over L lambda. All right. So it's basically just if it goes straight, the difference between the momentum if it goes straight through and the vertical component of the momentum if it goes through the other slit. And so that's what you need, but that means that the screen is going to have a position uncertainty given by h bar over that, which gives you this expression right here. And that is simply the spacing of the fringes of the interference pattern. So if you can detect which slit it went through by looking at the momentum, the uncertainty in position of the screen is such that it's going to wash out the interference pattern. Okay, so despite what Einstein thought, you cannot see both. And yes, a spacing of the fringes, so the interference pattern washes out. This was looked at in a really detailed quantitative analysis by Bill Wooters and Wojciech Zurek back in 1979. So the lesson is that the screen has a well-defined position, you get an interference pattern. If it has a well-defined momentum, you can have path information. Okay, then people decided to simplify the models. And the first people to do that were actually at City University of New York, Danny Greenberger and one of his students, her last name was Yassine. You've probably heard of Danny because you probably heard of Greenberger or in Zeilinger states, and also the version, sort of improvement of Bell's theorem. So the idea is we're going to really make things much simpler. So we have 2 paths, okay, and so it's a 2-state system, and there's a phase shift here, and it's basically a Mach spectrometer. And the particle can go up here and down here, and then we detect it when it comes out here. If we vary the phase, then we will vary the intensity coming out and hitting the detector. The visibility is defined as the maximum intensity minus the minimum intensity over the sum of the intensities. And we describe the state of the system inside the interferometer in terms of a density matrix. And it turns out the visibility is proportional to the off-diagonal elements of the matrix because that involves both paths. So that's what you need for interference. In terms of which path that thing goes on, well, if it's more likely to be in one path than the other, that would be one way of quantifying path information. So the rho 1, would be the probability that it's in path 1. The rho 2 would be the probability that it's in path 2. And so the difference between those two is how much path information we have. I mean, if it's equally likely to be in both paths, we have no information. If it's completely in this one and not in that one, then we have the maximum information. So we have visibility and predictability. And Danny and his student found a wave-particle duality relation that said that the predictability squared plus the visibility squared had to be less than or equal to 1. Okay, so that was really, I think, probably the first really quantitative wave-particle duality relation. And it was extended also by Greg Yeager a bit later. Now, the next step is to add path detectors. Okay. Now, what I just showed you for the path information isn't the way we usually talk about it. We usually say, okay, if I have a double slit and the photon goes through both slits, I want to have detectors there to tell me which slit it went through. We're not going to bias it by creating a state where it's biased in the path. We want to detect which path it goes through. So the idea is to put path detectors into the problem. So, I'm going to let theta1 be the state of the detector if the particle is detected in path 1. And theta2 be the state of both detectors if the particle is detected in path 2. And these states are not necessarily orthogonal. Their overlap quantifies how much path information we have. If they're orthogonal, we have perfect path information. If they're collinear, then we have no path information whatsoever. So the state of the particle and the detector looks like this. It's an entangled state. So if the particle goes through is on path 1, the detectors are in state eta1. If it goes on path 2, they're in state eta2. And the fact that non-orthogonal states cannot be distinguished perfectly means that that it is basically their indistinguishability is a statement about the path information. So if we want to measure them, though, we have to decide a strategy to do so. So we can't determine which state we've got perfectly. So one strategy is to minimize the chance of making a mistake. Okay, so this is the so-called minimum error state discrimination strategy. So we have two states, eta1 and eta2. They're not orthogonal. We can't perfectly distinguish them. So we're going to adopt a strategy that minimizes the probability of making a mistake. Okay, and I'm going to let PS be the probability of successfully discriminating those two states using the minimum error strategy. And I'm going to call something called the distinguishability. I'm going to call this probability of successfully distinguishing them minus the guessing probability. So if I had no detectors in there, I just guessed which path the thing was in, I'd have a chance of 1/2 of being right. So I'm going to subtract off the guessing. So this is basically the extra information that the detectors give you. And you find that the distinguishability plus the visibility is less than or equal to 1. So I think everybody recognizes that name. Okay, okay, that's one of these. It's really one of the seminal papers in this whole field. Okay, because I mean this model with the detectors and the detector states that are not orthogonal is really good. And it's pretty much been the model that everyone has used since when they talk about wave-particle duality. Okay, so then an obvious thing is what happens if we have more than two paths? And that turns into a mess, okay? So the first attempts were really kind of messy. I think it was Stefan Dürr. I mean, he did a major effort in this. And so the first problem is, what do you use for the visibility? Because now we've got a whole bunch of paths and we've got a bunch of phases. So how am I going to deal with this? So his solution was to look at the output intensity and to average over the phases, intensity and the intensity squared. And he came up with a visibility like this, and then you have the elements, the off diagonal elements of the path density matrix squared, and this visibility defined this way is in fact between 0 and 1. And then he had to come up with a some kind of a predictability. That really got complicated. So he sort of first looked at a particular state of the path detectors and looked at the so I think it was the P thing, the distinguishability, and then he averaged over the states of the path detector. So it really got rather complex, and but he did get a relation out. The next step was taken by my colleague and his postdoc, Janos Birgu and Matthias Jakob. So this one, excuse me. So we have 2 qubits. The first qubit is the particle. Okay, so the 0 is one path, 1 is the other path. The second qubit is the path, excuse me, the path detector. The particle density matrix is, I just trace out the detectors, so trace out the 2 part of the state. And then we have an extra element here, which is a concurrence, which is an entanglement. Angle the detectors and the particle R inside the interferometer. And for a qubit, the predictability plus the concurrence plus the the visibility squared are actually equal to 1. It becomes an equality instead of an inequality. They generalize this to higher dimensional situations, and then you're back to some kind of an inequality. But in the qubit case, you really get a very nice equality. Okay, so now, as promised, I'm going to talk about quantum resource theories and how those things fit into wave-particle duality. So first, I just want to give a little review about quantum resource theories and what they are. So for quantum resource theory, you need 3 things. You need a set of so-called free states that do not possess the resource. So these states you can use for free. You also have a set of free operations, and these operations do not create the resource. And then the last thing you have is a measure of how much of the resource a given state possesses. So I'm going to give you 3 examples of this. The first one, and really where the ideas were developed, was in the case of entanglement. So the free states are separable states. So a separable state looks like that. You only have classical correlations between system A and system B. The free operations are LOCC operations, so local operations and classical communication. What that means is you've got Alice and Bob. So Alice has half the state, Bob has half the state. What they can do is they can do local operations in their own laboratories, and they can talk on the telephone. So, right, but they cannot send qubits back and forth. All right. So they cannot send quantum information. They can send classical information and do local operations in their own laboratories, and that is LOCC operations. The entanglement measure, and these are pure states, is what you do is you say calculate the reduced density matrix of the A system by tracing out the B system, and then you calculate the von Neumann entropy of the A system. I mean, if you trace out the A system instead of the B system, you get the exact same answer. All right, so the von Neumann entropy of one of the reduced density matrices is a very good measure of the entanglement of the state. So this is sort of the first example of a quantum resource theory. Another one is a so-called group asymmetry, and this has to do with channel discrimination. All right. So I have a group G, and I have a representation of G, which is U of G, okay? And G is the elements of the group. The free states are the states which are invariant under the group operation. The free operations are covariant operations where if I operate on the state with the acted on with the group operation, that's the same as the group operation acting on the mapped state. And then finally, the measure of the asymmetry is the probability of successfully discriminating all of these states. Okay, and this idea was due to Marvian and Speckens. Now, where this is useful is if I have the channels that are described by U of G here. Okay, so I take a state, I shoot it into the channel, and for each group element, I have a channel. Okay, so if the group has n elements, I have n channels. And the idea is I want to be able to tell, someone gives me one of the channels, and I want to be able to tell which one it is. And so some states will be good at telling me which channel I've got, and other states will be terrible. So just as an example, I mean, if the states are invariant of the group operation, then all of the channels are going to give me the same output. And that is going to, that's terrible. Okay, so those states have no asymmetry. So ideally, what I would like be a state with high asymmetry that gives me very different looking outputs for every different channel. And so I want an input state that's going to give me lots of different outputs. So this is known as asymmetry. And so the next thing we're going to look at is coherence, and that's the one that we are going to be making the most use of. So this concept is basis dependent. So you specify a particular basis. That's what you have to do from the beginning. I mean, when we start talking about duality, the basis is going to be the path basis. All right, so that's going to be our preferred basis. The free states are states that are incoherent states. They are diagonal in the preferred basis. The free operations look like this. So here's an operation acting on the state, and you've got your Krauss operators, and the Krauss operators map incoherent states to incoherent states. They will not create any coherence. This theory is due to Baumgratz, Kramer, and Planio, 2020. And then the thing that we're really interested in is the measures of coherence. Okay, so the idea is what we're going to do in the wave particle duality is we're going to replace visibility by coherence. All right, and then see whether we can get a wave particle duality in terms of these coherence measures. So they approach the problem by saying, okay, what kind of properties do I want a coherence measure to satisfy? Well, first of all, I want the coherence to be zero if the state is totally incoherent. All right, that's pretty clear. For coherent operations, you want to make sure that the coherent operation cannot increase the amount of coherence you have in the state. All right, and it should be non-increasing underneath the state. And they found two measures that satisfy these criteria, and we're going to make use of both of them. First one is so-called L1 measure. So what you do is for a given density matrix, you take the difference between it and an incoherent state, and then you take the minimum over all incoherent states. That looks like it might be kind of difficult to deal with, but it turns out that it's actually very simple. It's simply the sum over the absolute value of all the off-diagonal matrix elements of the density matrix. So that's one. The next one is a relative entropy measure. Okay, so in that case, the idea is the same. So I start with my density matrix that I want to specify how much coherence is in it. And then I take the relative entropy between it and an incoherent density matrix, and then I take the minimum over all incoherent density matrices. Again, that looks like it might be a mess, but it's actually rather simple. It's just the von Neumann entropy of the diagonal part of this density matrix minus the von Neumann entropy of the entire density matrix. Okay, so the diagonal density matrix is I just take the original density matrix and just keep the diagonal part. Okay, and So let me just say a little bit about relative entropy. The relative entropy of two density matrices is given by trace rho log rho, the first one, minus trace rho log sigma. Now, the relative entropy isn't a distance, but in many cases, it kind of acts like one. Okay, it doesn't obey the triangle inequality, so that's why it's not an actual distance. But I mean, you'll notice if sigma is equal to rho, then this is going to be zero. So if they're the same, it's zero, and then sort of the more different they are, the bigger their relative entropy is going to be. It's really an entropic, sort of an entropic distance. And this is from the set of incoherent states. Okay, now there's actually a connection between group asymmetry and coherence. So let's just consider the cyclic group of n elements. Okay, so it has a generator A, and the group simply consists of A to the J for J 0, 1 through N. So A to the 0 is the identity, and A to the N is also the identity. The irreducible representations of this group are one-dimensional, and they look like this. And there are n of them if there are n group elements. And suppose we take a representation, which is just the direct sum of all of the irreducible representations. Okay, so that will give us an n-dimensional representation of the group. And so then if n is a pure state, the probability of distinguishing the channels described by this representation of the group is given by that minus 1 over n. There should be a 1 over n factor over here. I just realized that when I was looking at it. So, so this is the probability of being able to distinguish the channels from this group. So that's group asymmetry, and that's directly related to one of the coherence measures of the density maker. So there's a close relation here between the group asymmetry and the coherence resource theories. Okay, so now let's look at coherence as a resource here. So okay, we've got this fancy definition of coherence. What's it good for? I mean, does it actually tell us anything that we would like to know about? So the Deutsch-Jose algorithm is kind of was one of the first algorithms that people came up with in quantum information. The idea is the following: I have a green box here instead of a black box, and it evaluates a Boolean function. Okay, so f of x is an n bit binary number, and f of x maps x to either 0 or 1. Okay. And in the Deutsch-Jose algorithm, you're promised that this particular Boolean function is one of two things. It's either constant, or it's the same for all inputs, or it's balanced, which means it's 0 for half the inputs and 1 for the other half of the inputs. Okay? And you would like to know which. And we would like to determine this with as few uses of the box as possible. And I mean, classically, you have to put in at least 2 values of x to see whether this thing differs, whether you've got different values or not. And you might have to put in a lot more if you like. Right. You would put in a lot of x's and they don't come out the same, and only sort of at the very end might it differ, and then it's a balanced function, it's not a constant function. The quantum algorithm, only one use of the box is required to give you a definite answer. So that's the standard Deutsch-Jose algorithm. So how does coherence come into this? Well, the ideal input state for the Deutsch-Jose algorithm is like this. It's a sum over all possible inputs for the x. And then you have this auxiliary qubit that does nice things. So we're not going to worry about that part. Suppose, however, your input here got corrupted. So suppose it interacted with the environment. So that means that it got correlated with environment states. So this is bad. Okay, we don't want any correlation between this x. We want it to just be a nice superposition. We don't want it correlated with anything. And so this is basically a noisy input. So what that's going to do is it's going to give you the chance of making a mistake. All right, if you've got a corrupted input. So, okay, so what is the probability that you are going to get the right answer as opposed to making a mistake? Well, if you work it out, probability of getting a right answer is just 1 over n times the L1 coherence of the density matrix you get if you trace out the environment from this x eta x thing. So that gives you a density matrix. You calculate the coherence of that density matrix, multiply by 1 over n. That is the probability you will get the correct mean. So if there's no corruption, CL1 is just n, and your probability of the correct answer is 1. But the worse this gets, the lower the probability of getting a correct answer is going to be. So this gives you a direct connection to of coherence to a quantum algorithm. Okay, so now let's look at wave-particle duality and see how we do this. So now we're going to take sort of extended Verdi situation. So we're going to have n paths, and the probability of being in each path is going to be pj. So this is a path state, and then we have the detector states over here. And we'd like to see if we could get some kind of a wave-particle duality out of this particular state. So the path density matrix, take this thing and trace out the detectors. And I'm going to be interested in the coherence of this path density matrix. So if I use the L1 measure of coherence, I'm going to take x. I just take 1 over n times the coherence measure of the path density matrix. For D, this is something the probability of successfully discriminating the detector states. So if I give you one of the detector states, and I want you to tell me which one I gave you, this is the probability that you would be able to get the right answer. So this is basically the probability that the detectors are going to tell you the right path. And again, I subtract the guessing probability, which in this case is 1 over n instead of 1/2. And then when I do that, I find a duality relation, looks like this. The path information here squared plus the coherence squared is less than or equal to 1 minus 1 over n squared. So again, if you can very successfully figure out which path you've got, your coherence is going to be really low. If your coherence is really high, you're not very successful at figuring out which path. Now, that I'm going to skip. Okay. There's also an entropic version, so we can also use the entropic measure of coherence. So in this case, I've got two random variables. I've got d, which corresponds to which path the particle took. I've got m, which corresponds to the result of the detector state measurement. I mean, ideally, I would want these things to be completely correlated. Then measuring the detector would definitely tell me which path the particle took. So if the probability of that d is equal to j is pj, the probability that n is equal to j is qj. Then I have a joint distribution pjk, which is the probability that j and d is k. I can define a number of quantities here. First one is the Shannon information of the path variable, which is just given by this. The second is the mutual information between the measurement and the path. And that's given by Shannon information of path, Shannon information of detectors, minus the Shannon information of the distribution. If n and d are uncorrelated, in other words, if the detectors and the path are completely uncorrelated, the mutual information will be 0. If they're perfectly correlated, the mutual information will just be the same as the Shannon information of the path. And what you find is that the relative entropy measure of the path plus relative coherence measure plus the mutual information between the paths and the detectors is bounded by the Shannon information of the path information. So you also get an entropic information. This was actually looked at experimentally by a group in China. So they looked at the case for two paths, and this is their apparatus, and their idea was the path was the path, and their detector states were polarization states of the photon going through. So you could correlate the polarization of states of the photon with paths, and they actually measured the pairs of and also the mutual information between the different paths, and then they added them up. And in this case, we're talking 1 bit, so the added information is just 1. And you can see that when you add these two curves, you get something that stays below 1 as it should. So this stuff actually can be done in an experiment. Okay, just to mention a second strategy that you can use. So far we've been talking about minimum error strategy for measuring the path information. We've got the detector states that are not orthogonal, and we come up with a measurement that minimizes the mistake. Another kind of measurement called unambiguous discrimination, in which case you always get the right answer, but the measurement can sometimes fail. Okay? And in that case, what you want to minimize is the failure probability. And there is a so if I use unambiguous discrimination instead of minimum error discrimination, that's the probability that the measurement succeeds. Sometimes it will fail, and you get a wave particle duality relation that looks like the success probability plus the L1 coherence has to be less than or equal to 1. This was done by a group in India. They were actually the first ones to apply these sort of resource theory ideas to wave particle duality. Okay, so the next thing I'm going to talk about are duality games. So, and this was pioneered by Patrick Coles, Kanievsky, and Stephanie Dugan. So we got 3 parties, Alice, Bob, and the house. And what happens is the house prepares one following states for Alice and Bob. So here's our basic state, paths and the detectors and the probability of being in different paths. And then what the house does is applies a particular set of phases to the paths, all right? So it applies one of these operators here, so you can see it's applies a phase to each path state, and which phase it applies depends on which operator used here. So you can think about what this is down here is sort of putting a phase mask, the paths, and so one of these states is going to be presented to Alice and Bob, and they don't know which it is. So Alice has access to the particle inside the interferometer, which means that she has access to these states here. Okay. Bob has access to the A to J's. Bob has access to the detectors. And now the house flips a fair coin, and that's going to determine which of 2 games Alice and Bob have to play. So the first game is called phases. And in this game, Alice tries to determine M. She tries to determine which set of phases were applied to the state. And then Bob does nothing. And they win if Alice is right. So they're called E phase, the probability of winning phases. So that's trying to figure out which set of phases was applied to the state. Next one is called ways. That, of course, is going to be about paths. And so in that case, Alice measures the particle to determine which path it took. So then Bob measures the detectors, and they win if they agree. So P ways is equal to the probability of being able to distinguish those detector states. And so the probability of winning the overall game is 1/2 P phase plus P ways, because the house has flipped a coin, probability of half, so the probability of half they play phase, and the probability of half they play ways. Now, Their ability to win this game is influenced by the duality relation, because the probability of winning being phased depends on the coherence of the path density matrix, this thing X. So the lower the coherence of the path density matrix, the lower the probability of being able to win the phase game, and of course the X is wave-particle duality. So if I take into account the wave-particle duality relation that I showed you, and then find out what's the probability of winning the overall game, you find out basically that it's square root of 2. So they can only win the game. They can't win it every single time. They'll win a certain fraction of time. That would be 1 over square root of 2. So that inequality is perfectly okay. It's valid, but you can actually do better. It's not tight. And then the cost of better is a considerably more complicated wave-particle duality relation. So let me show it to you. So you can see it's a lot more complicated. So that previous bound was too weak, and we can do better, but we need a new duality. So that's pretty opaque. In order to make it less opaque, let me show you a picture. But this inequality is tight. There are states that actually saturate this inequality, which was not true of the previous one. So what in the world does this mean? So I'm going to let X equal a normalized version of the coherence, and I'm going to let Y equal a normalized version of the ability to distinguish the detectors. All right. And then I can go to this basically gives me an allowed region for these two things in the XY plane. So what does it look like? It looks like this. Okay. So the way this works is, so for n equals 2, it's 2 paths. The allowed region for X and Y is the circle here. So it's the union of the green, yellow, and orange regions. All right. And any point in there corresponds to an actual state. As n starts increasing, the region shrinks. So for n equals 9, we just get the orange and the yellow regions. And then as n goes to infinity, we just get the orange region. So what the wave-particle duality relation does is it gives us a region in this XY plane, which is coherence versus path. And the points have to lie in here, and it depends on how many paths I have. And now if I take this fancy new wave-particle duality relation and I calculate the probability of winning the game, the winning probability, instead of being 1 over square root of 2, becomes 1/2. And there are states that achieve that. Now, the last thing I'm going to talk about, we're still going to be talking about the game, but we're going to change the rules. So suppose we modify the game, and we want to require less information, Alice and Bob, in order to win it. Can we find a situation where they can always win the game instead of having, say, a probability of 1/2 of winning the game? So here's how I'm going to change the rules. And so to play ways, I'm going to let Bob name 2 paths, one of which is the same as the one Alice found. So basically, Bob gets 2 guesses as to the path instead of having to get it absolutely right with just 1 guess. And for phases, I'm going to let Alice name two sets of phases, and one of which is the right one. So the question is, if I sort of loosen the rules like this, can they always win the game? And it turns out that for this particular case, for the case of 3 paths, they can. So let me just sort of show you how it works. So here are the states that the house gives to Alice and Bob. M has values 0, 1, 2. Okay. So there are 3 possible states that they could get. And for the detector states, I'm going to make a particular choice. Choice is going to be these things called trine states. These are qubit states. In the 0, 1 plane, they make an angle of 120 degrees with each other. So one point's along the x-axis, one point's like this, and the other one points like that. They have an angle of 120 degrees. I also want to define the anti-trine states. So I'm going to need those for measurement. Okay. The anti-trine states have the property. They also make 120 degrees with each other, but they are orthogonal to the trine states. So 0 bar 0 would be 0, 1 bar 1 would be 0, and so on. So the anti-trine states can actually be used to eliminate possibilities of trine states. So I'll show you in a second. Okay, so if they play ways, in other words, Bob needs to measure the detectors to find the path. What he's going to do is he's going to measure a PU of EM based on the anti-trine states. Okay? So, for example, if he got 0, then since eta bar 0 is orthogonal to eta 0, that means that Alice definitely did not get the result 0. So if Bob, using this PU of EM, got 0, he knows Alice did not get 0, so he can say she must have gotten 1 or 2. Those will be his 2 guesses. He announces that, okay? And that's guaranteed to be right, okay? What about Alice? Okay, so if they play phases, what is the situation? So I just trace out the Bob part of the state, trace out the detectors, and then Alice ends up with one of 3 density matrices. Okay? These U's are an orthonormal basis. So the first density matrix, if m is equal to 0, just has the support U1 and 2. Has U0 to U2. 2 has U0, U1. So what Alice can do now is she can measure the density matrix she's got, which is guaranteed to be one of these 3, U0, U1, U2 basis. So what would happen? Well, if Alice measures, suppose she gets 0. I can take a look. If she got, that means she got U0. Okay. There's a U0 here and there's a U0 here, but there is no U0 here. So that means that what the house sent must have either been 1 or 2. So if she gets if she measures when she gets U0, with a guess psi 1 or psi 2, those are guaranteed to be correct. And so she announces those 2, and in that case, no matter whether they play phases or ways, they can win the game. Again, because we've required less information of them. So let's look at one last thing here. Now, how much information is too much to win the game? Okay. Well, then you can look at this in terms of mutual information, and apologies for using a different symbol for this set of slides, and I didn't notice that H back there. Okay, this is mutual information again. Okay, so this is mutual information between the 2 random variables. X1 is the phase that was sent, and X2 is the phase that was measured. And then Y1 is the Alice path, the one that Alice measured, and Y2 is the path that Bob measured by measuring the difference. The sum of those 2 mutual informations has to be less than or equal to log 2n, where n is the number of paths. So just as an example, perfect phase correlation would imply that the mutual information between x1 and x2 was log 2n. Looking at this inequality, that would mean the mutual information between the paths would have to be 0. So, so perfect phase correlation implies 0 path information. And vice versa. In the example we looked at, the sum of those 2 mutual informations, in fact, log 2 9/4. In that case, n was 3. And log 2 9/4 is in fact less than log 2. So, using this inequality, you can actually find out how much information is too much, okay, to always win the game. And so that is, nobody was ever finishing a little early. So, so just to summarize, Alice performed a measurement to outcomes corresponding to phases. Performs one that corresponds to pairs of paths, so pairs of phases. And then for the three path case, we find that the path information, the phase information isn't less than log 2(3). So to conclude, wave-particle duality relations have a long history going back to Einstein-Bohr. Many people have made significant contributions along the way. And the resource theory of coherence, and I would maintain a useful addition to the analysis of wave-particle duality. And we can't get partial wave and partial particle information from a state as long as we don't ask for too much. Okay? As long as the sum of the wave information and the path information is below a certain upper limit, you can always win the duality game, which is a way of saying that you can have some path information and some wave information as long as it's not too much. Thank you.